Welcome everyone to Danilo from EPV Technologies session. My name is Nathan Appleby from Inspired Solutions and I am chairing today's session. I'm going to hand it over to Danilo, who is happy to take questions during his session. And we'll take questions during, but there'll be some time at the end as well. I'll hand it over to you now, Danilo.
Okay, thank you. So hello everyone, and again, this was a recorded session, but we did the test before and it looks like the audio is going back and forth. So at the end, instead of doing the recorded session, I will do it live, and I hope I will remember everything that must be said. And again, as Nathan already mentioned, if you have questions or if we can make it a live session, that would be very great. I have to say, I can't see the moment where we can meet again in the future because I had enough of these virtual sessions. But okay, that's me. Okay, so my name is Danilo Gipponi. I work for EPV Technologies. I will not speak much about EPV Technologies in this session. So this is a technical session, and the title is "Are you wasting money because of storage into instruction stream?" This is session 6 a.m. And okay, here I leave it to you for read. I guess you had enough of this because every paper is supposed to have this at the beginning, so you know by now what you have to do. And I go to the paper. Now you see, I have to shoot it down because it starts automatically. And again, it looks like when we did the test before that the sound was going back and forth using the computer. So I will do it this way. So you will see also my editor, and I'm sorry for the inconvenience. So this is the title of the paper, and this is the agenda. So I will make a short introduction, and I will make an overview of what is a storage into instruction stream. And then I will mention about evaluating the impact, identifying who are responsible for eventual problems with this topic, and then conclusion, and finally the question. Okay. Oh, this is anyway, compared to the time I've been given, a short paper. I don't think I will take all the time, unless a big discussion will start with you. So let's make the introduction. Big part of performance analyst time is dedicated to tune components and applications that use some amount of CPU. This is why the CPU usage is the driver of the costs in all possible ways on a mainframe, on a ZOS system. And so it's very important to understand who is using the CPU. And this was true with the old way, or let's say the way it's been used in these last years, that was using the 4-hour rolling average. So you wanted to make sure that in the peak hours, there were no one that would waste cycles. And in a way, it's again true in the future with tailored fit pricing, because at that point, all the CPU used on your system, even the one that is running outside of the peak hours, will be summed up to make up the count at the end of the year. So it's very important to understand if you are not wasting CPU cycles. Again, let's say that in these last years, the work of everybody has become very peculiar. Let's say because we are intelligent people, we don't like to waste our time. So we were mostly focused on the peak hours, and we were lazy on the other hours. And again, this is a symptom of intelligence, and it's true in most of the sites. So everybody would focus on the peak hours And as an example, on Saturday and Sunday, you would open all the reorg or all the possible batch, because anyway, that CPU consumption wouldn't sum up to the bill at the end of the month. And so nobody was really looking into that time frame to find out if there were wastings. Again, now the situation has changed a little bit, because now you pay for the whole amount of the CPU you consume at the end of the year, if you are in tailored field pricing with the enterprise consumption solution. And so let's say that it's become eventually even more important to make sure that there are no cycles really literally wasted. Okay, so what's happened with the new release of hardware that IBM has identified the store into instruction stream issue as a possible reason for, let's say, first of all, reduction of the processor cache effectiveness. And as a consequence, a significant increase of CPU utilization. So now we will go into some detail to explain why this is happening, if it is happening. So if there are specific situations, this could happen. And if it happens, you will see what you have to analyze in order to understand if it's really this kind of problem. Anyway, the problem was definitely there. So let's say IBM introduced new hardware that was very efficient on specific situations, but there were situations that were very strange. And at the beginning, it was not easy to explain why there were so many cycles wasted without anything happening. And again, this SIIS has been identified as a possible reason. So after the overview, we will provide the formula that you should use and some examples to help evaluate the amount of MSU that you are wasting because of this situation. Okay, so the CPU consumption strongly depends on how your application code fits the processor cache design. And also, I have to say, on the concurrency or on the fighting that you have to have with other helpers and other applications in order to get your shared resources. So the processor architecture of modern IBM machine expects to execute code with respect of the following rules. So there must be separation of data and instruction in different cache lines. And there must be localization of storage reference. And this is let's say, the hint of this specific situation. The code must not be self-modifying. Now, because I recorded this session some time ago, I don't remember what is going on the next slides, but anyway, I will not add anything now, but I will make you an example of a self-modifying code so that everybody will understand what I'm talking about. So if a program violates these rules, storage into instruction stream event happens. So what happens literally is that the instruction need to be refetched from the level 3 cache. And you know that when this happens, the CPU is spinning and you are wasting cycles. So it's like you are in a situation where you could work, but instead of working, you have to wait because something must be refetched from the level 3, and then you will start working again. Just because this is the overview, but I assume that everybody knows that the further away you go and the more CPU cycle you are wasting. So a level 3 cache is much worse than a level 2 or a level 1, and going on, the level 4 would be even worse. Okay, so this is a Z15 cache architecture, and you see that on the level 1 and on the level 2, you are very close. And in fact, you do not go into the nest. As soon as you are in level 1 and level 2, you know that now the relative nest intensity is very important to understand how good you use your machine. And this is the amount of data available for data and instruction at the level 1 and the level 2 in the table below this short graph. Again, this is an introduction. I assume everybody knows this by now. But again, if you have questions, feel free to put them forward. And by the way, because now I'm speaking, so this is not a recorded session, if here and there someone would drop a cough or something just to say, so I understand that you are there, I'm not talking alone.
We're still here, Danilo.
Okay, thank you. Okay. Okay, this is a graph that shows you the percentage of level 1 miss with a Z15 in a production system. So this is real data. It's a situation that could represent yours. And you may see that it's very low numbers we are talking about. It's like 2.5% of the times you do not find what you are looking for in the first level of the cache. Now, it's very incredible when you think about the fact that this low amount of level 1 miss is what really makes your ZOS hardware wasting so many cycles. So the big, huge difference is that when you make just a 1 miss out of 100, still that miss could cost you a lot of money. And again, taken from this, let's say, model, this again was a production system for a bank. And again, this is very representative. It's a generic figure of what happens in many sites. So it could really represent also yours. And you see that when you miss on the level 1, again, still 70% of the time, you can find what you're looking for on the level 2. And that, again, is a very good situation. When you are in level 1 and level 2, you do not need to go into the nest. And so you are not wasting too many cycles. You're wasting a little bit if you go at level 2, but that's not a bloody miss. When you go into level 3 or worse, higher levels, then you are really there spinning your CPU cycles, and every second really counts and make you pay more and more. And this is what you want to avoid if possible. So this instead is not real data. So the 2 slides we saw before were real data from customer. This is more of a projection. But the projection, again, based on real numbers, is that, as you may see, the more you go further on the level cache, so at the level 3, at the level 4 local, at the level 4 remote, and then in memory, or the worst case at all, in memory remote, you pay literally twice as much, 8 as much, 16 times as much. So you are really increasing exponentially the cost of the activity that you are doing just because it's not there close to the CPU. Now, the situation is that the modern compilers produced by IBM has been written with this processor architecture in mind. And so this doesn't happen, or better, the SIIS problem doesn't happen with the new code. But the one real problem, or let's say one reality in our world, that there are still programs running on our system that were written the last millennium, and they are very old. They were written in assembler, and they've worked always very fast and in a very good way since they were written on the last century. So there are these kind of programs around in many sites. Luckily, not in all the sites, but in many sites, there are still these programs running. There is a paper that is IBM Z system remediation of program with storage to instruction stream impacts by Katie Walsh, that tries to explain what are the situations where a program written by a user, so something that your development team developed again in the 80s, 70s, 90s, and now this could result into this kind of problem. But we have found out that possible bugs are also there with code written by IBM or independent software vendors. And the reason is that this code was excellent with the old architecture. It's just now that it doesn't fit with the new architecture. So we will see the example in a few slides, and you will understand what I'm talking about. Okay, so before I go forward, or better, I go forward very quickly just to find, okay, no, then I go back to the slide where I was, and I will make here just an example of something that I have very in mind about what we do. So we, in EPV, let's say one of the main activities that we do is that we read the SMF data. And there are situations where the code to read the SMF data may vary depending on outside situation. And the easy example to make is the MCT of the kicks regions. So you may say in production that you want to write everything about what's happening with the transaction, or you can customize the MCT and telling that you are interested only in the very important columns and fields. So you just select the CPU consumption and I don't know, the response time and whatever. But it's a very common practice to change the MCT. Now, a program that is running nowadays, in order to read that SMF record, first of all, must understand what kind of definition you have made in order to make sure that you read the exact fields in the exact position. And again, if you change the MCT, this could change the position. So what could do a program? Could, first of all, read the MCT definition, then assemble in memory in that point in time the program in order to read correctly what has been written into SMF, and then go forward. Now, this is a specific situation where the storage into instruction stream becomes an issue, because you are creating the program in memory, but as soon as you create the program which is there in that very moment is written someplace, and then it must be fetched. So the program must go, first of all, write the program, and then must go and fetch it. And while it is fetching this program, it is spinning away. This is I hope I explain it in a good way. This is a very easy example of what could happen with this topic. Okay, I will go forward if there are no questions. So in order to evaluate if you have this kind of problem in your system, first thing you have to do, you have to evaluate the impact. if this kind of problem is there. And so you have to calculate a percentage SIIS index that will represent the percentage of level 1 instruction cache miss due to this specific topic we are talking about. In order to do that, you need to have basic and extended counters that are available in the SMF record 113. And these are the formula that you have to use. And again, this is, I assume you know this, but anyway, let's say that this, especially the extended counters, they change it from hardware to hardware. So the formula could be slightly different when you use different kind of machine. Now, only in the recent version, they have stabilized the extended counters. But you may see in this formula that you have to use for 3 different type of hardwares, for a Z13 or a Z14 or a Z15. And you see that in the first of the 3 lines, you have to use a different extended counters in order to calculate this kind of index. Anyway, make sure that you use the right counter, the right extended counter in your situation. And then the formula is very simple. So you use the value you find in the field E163, so extended 163 for a Z13 machine, divided per the basic counter number 2 and multiplied by 100. And now you will find an index, and this will give you exactly the idea, the proportion of how many times you need to go away to fetch data and instruction because of a storage into instruction stream problem. Okay, this other slide is just explaining you why you have to use 2 different extended counters when you are on a Z13 or on a Z14 and Z15. So it's just a reprise of what I said before. Now, taken from a paper from John Berg, and you see the title in the note at the bottom of the page. Let's say that the figures you find here are really reasonable, so I don't think there is much to think about that. So ideally, if you have an impact that is lower than 2% of this kind of problem, then you can forget the problem. It doesn't make any sense to spend more time because the impact is negligible, and whatever activity you will do, you will have very little gain. If you are between 2 and 5, then this is a low priority kind of situation. And again, this is the suggestion from John Berg. If it's between 5 and 10, it's an average situation. So you could have some advantage or not. If it's higher than 10%, then you definitely need to spend some time in order to understand what's happening and see if you can fix it. And we will see later on that also understanding that there is a problem, it doesn't automatically help you solving the problem. There will be other issues. But again, this is going on with the rest of the paper. Okay, so this is a table taken from our tool. And you see that the last row, the one circle in red, contains values. And in this situation, we see that the value is always very low. So in this, again, real example, this could be, let's say, skipped. You shouldn't spend too much time looking into it. But now we will go some real example and see some situation where the problem is there, the problem is significant, and let's see what you can do. So if there is a situation where there is only one address space that is causing the issue, you may try to find it out looking at the top consumer in the hours when this index was higher. And if you find it, then that's the lucky case. That's the best option you could have. So let's say you have hours where you have this index that is very high. You go and see the top consumers and you immediately spot them. If this is not the situation, then there is another activity you could perform, and we will talk it about in few slides. And this is using the instruction count matrix provided in the record SMF30. And this is not something automatically available. So if you want them to be turned on, you have to change the parameter in your SMF PARM member, in your PARM library. And the default is no count, so no SMF30 count. So you have to change this parameter if you need to have the counters at the address space level. Okay, so let's have a couple of real examples. So this is a lucky case. So we had a situation that on the 4th of June of 2020, this is the slide we have available here. We had this index we were talking about before that was higher than 10% in two specific hours. At 20 and then 21, you see it was slightly higher than 12%. So in those 2 hours, definitely there was something running on the system that could create this situation where the system was spinning because there was a storage into instruction stream topic or issue in the code running at that time. Okay, so we go to the next table, and what we do is that we go and look at the address space level. Now, because this is some real data from some customer, we have obscured some of the lines and try to cover the name. But you see that there was a batch job that was something, and then HSM A110 that at 8 and 9 o'clock in the evening was using a lot of MSU. Now, this table here is showing the MSU at the address space level. And you see that, okay, the first one was something was running throughout the whole day. And instead, the problem we had at 8 and 9 o'clock, and there was just an address space that at 8 and 9 o'clock was using a lot of MSUs. And so this was probably the critical, let's say, the culprits, as we say here. So we found it out immediately. Okay, and so the next step was to try and see when this address space was running. And we saw that every time that specific address space was running, the index about the storage into instruction stream grew about 10%, or anyway, every time the address space was running, there was the problem. So definitely this was the address space. So what is this job doing? It's performing auditing of HSM controlled datasets. So the customer at that point identified the problem, opened an issue to IBM, and this is literally the answer they got from the support from IBM. And I read it for you. We absolutely agree with you that this area needs some work based upon your findings in order to increase performance. This is the first time we have had this reported, so thank you for alerting us to it. Since this is not a bug, so the program is still working, you could open a request for enhancement for improvement in this area, and then we will feed the work into our schedule. So we found out the problem, we found out what it was, and this was an IBM problem. And again, this is their answer. Let's now have a look at another example, and this other example, it was not that easy. It was not as in the first case where you noticed the problem and you immediately found out the address space responsible for that. Okay, so as I told you, you need to turn on the SMF30 counter, and this will tell you for each address space what's happening within the architecture of your cache machine. And let's say that the address space CPU cycles can then be calculated using the formula that you see in the slides, and the slides are available, so you can download them from the GSC site. So again, in the previous slide, I'm going back one slide just to show you. This is the label of all the fields available, and this is how you use them in a formula in order to understand the CPU cycles used by every single address space. So every single address space cycle per instruction, so the average number of cycle per instruction, can be estimated using this other formula. So you have the CPU cycles and you divide them for the instruction that were executed throughout that time. So if you have an address space that shows a very high cycle per instruction in hours, when the index of the percentage SIIS is high, then they are those probably that are responsible for the situation. So again, a real example. So this is another situation, another customer, and we see that we have in the morning at 1 and 2 a situation where the counters were worth some effort in order to understand what was happening there. When you just look at the top address space consumption, you don't find anyone in this situation that was linkable directly to the situation. So there was no one that was clearly the address space that was creating the problem. So we had to calculate the CPI values for all the top address space in the critical hours. And this is represented now in this table, and we see that, okay, we have changed the some of the name, and we see that the first hour, so the 5 top rows, there was a job 1 that was having a very high cycle per instruction rate. And in the second hour, there was another job that was the job _6, as we rename, in order to cover the data from the customer, that was having a very high cycle per instruction, much higher than the others in the same period. Okay, so the address space job _1 in the previous table was a backup of the Unisystem service files calling the IBM Tivoli Storage Manager, or the Spectrum Protect product. let's say that in this situation at this customer, there was a project already in place to migrate this thing to DFHSM. So already this was under Spectrum. So there were people already working to solve the issues related to this address space. So there was no other action to do. Instead, the one that was running at on the other hour, we found out that this was an old user-written assembler program. And the problem was that this was very old, very stable, used throughout years and years. There were a little documentation. The one that wrote the code was not anymore in the company. And so we immediately knew that something should have been done in order to fix this issue, but it was not an easy thing. So let's say that, because this is a real story, what happened then that at first they tried to understand how they could handle the situation. And then because of, I would say, organizational issues, they decided that they could, for the moment, accept the problem. So the problem was there, the problem was clear, but there was no way to replace this old assembler for many reasons. And so they decided to go forward with it. Okay, so I'm at the end of the paper. Let's say that the first thing is that if you measure, you know if you are in the situation. So just measuring, you may understand if you have this kind of problem in your system, and that in itself is a great advantage. So if you know that there is a problem, then you can try to do some action in order to fix it. To understand if there is a problem, you just need to collect and exploit the record 113 that nowadays everybody should have turned on. So it's years now that IBM say, if there is nothing else you do, when you go back and you understand you have not your 113 record of SMF written down, first thing you do, make sure that you write it down, because the effort is minimal and the advantages are many. And then again, you may be lucky, and if you're not, then you need to turn to do some action in order to understand the cycle per instruction at the address space level. So something more could be done. And that would be the end of my presentation. If you have questions, now is the right time. I hope you are still all alive and not snoring with your microphone closed. And again, if you have questions, you can put them forward now, or eventually later you can contact me. The paper is available on the GSC website, so you can download it. There is also a real paper, so a document available. So if you are interested in that, you can just let me know.
Thank you, Danilo. Do you have can you share your email address so that people can contact you?
Let me see. I guess it was in the first slide. I'm not sure, but I guess.
Whilst Danilo's finding his email address, does anyone have any questions?
There it is. On the first slide, let's say when there was the title, there was my email address. So everybody can contact me afterwards if they have questions or if they are interested in the real paper. So there is a document, a Word document or a PDF, better, that explain exactly what was the topic in this presentation.
Well, thank you, Danilo. It doesn't look like we've got any questions, but if anyone does come up with any afterwards, then and you'd like to get hold of Danilo, then you can get in touch with me or my co-chair Piara, and we can get in touch with Danilo. We can get you a copy of the presentation and the paper that Danilo is talking about. And if I could remind everyone to please give some feedback on this session using the session code 6am. That would be really appreciated. And if anyone is interested in joining the GSE raffle, you can do so by donating to one of the charities. And if you'd like information about how to do that, it was on one of your earlier slides, Danilo. And again, if this slide gives some information about becoming a member of the GSE UK, if you aren't already, again, you can message me or email me, Chiara, Danilo, or any of the other GSE contacts for more information about doing this.
So one comment I have for you, Nathan. I've seen that someone wrote down something, because I saw I have 4 notices of someone that wrote something down, but I can't read what they wrote down. So I don't know if those are questions or maybe just comments on the paper, or I have no clue.
I have one note saying, thanks, Danilo, great presentation. Apart from that, those might be direct messages to you, Danilo. I can't see any other ones, but if anyone, again, this last chance for anyone to ask Danilo any questions, and then we'll end the.
Because I got the information, I got the note, but for some reason, probably I'm just a dumb user of this Zoom application. I can't read the notes. So I don't know if there are questions. So let's say, if there are questions, please put them aloud so that I can try and answer them. Instead, if there are comments, I assume there will be all good comments. So thank you.
Well, we've had our friend Hartmut from Germany has sent another thank you. Oh, we've had a question, Danilo. Can you see the question from Raj?
But I don't see it. That's the point.
You can't see it. Okay.
Can you read it for me?
I will read it out. So the question is, hi Danilo, what is the CPU overhead of switching on SMF30 count? Is it something you would only switch on temporarily? Or is the overhead small enough to leave it on permanently?
Let's say that the overhead is small enough, but there is no other usage of it unless this specific topic at the point in time. So I wouldn't turn it on if you don't have an SIIS index that suggests you try to find out. Let's say that when they first introduced that in the SMF30, the expectation was great, but afterwards there was no real great advantage in knowing the cycle per instruction of every single address space. And so it was, let's say, the expectation somewhat fell down. So my suggestion, personal suggestion, is that if you don't have the issue, I don't see why you should turn it on, even though it's negligible. It's not wasting many cycles. It's just one more field in an SMF record. But then the point is that if it's useless, then my suggestion is don't do it. Instead, make sure that you have the 113, because when you have that, you can calculate the index. And with the index, then you may take the decision to turn it on.
Does that answer your question, Raj? Raj said that's great. Thanks, Danilo.
Okay, thank you all, guys. And
excellent. Well, we'll end it there then, Danilo. Thank you, everyone. Again, if you have any more questions, please get in touch. And our next session is going to be at 10:30. So I hope to see you all again. Speak to everyone soon. Thank you.
Okay, thank you.